So chapter 6, I should say, chapter 6 is all about rational expressions, and rational expressions means that we're going to be now seeing polynomials that are in fraction form. Rational means in a ratio is a fraction. So a rational expression is a fraction whose numerator and denominator are polynomials. An example of what I mean by that is like this first example here, 3 over x plus 4. That is a rational expression because it's a fraction and we have polynomials in the numerator and denominator. Even though 3 is just a plain number, because the x plus 4 in the denominator, that would be considered a rational expression. Same with 2x over x squared minus 4x plus 4, and x squared minus 5x over x squared plus 2x minus 3. So what's nice about this chapter, for some of us, I guess, not everyone, but what's nice about this next chapter coming right after chapter 5 is we pretty much know all of the prerequisite information to solve these types of problems, because what we're going to be doing is taking these rational functions or rational expressions, we'll be factoring them, and then we'll be answering different questions based on their factored form. So this chapter is going to be a nice transition from chapter 5 because we're still going to be factoring, so you're still going to need all of those skills from the last chapter, but now we're going to be applying them to a little bit more challenging situations. One thing that we do need to recall is this word here, the domain. So the domain is the set of all of the numbers that work for the function, basically. So the domain is going to be any x number that will work for the expression. So to write that in the best way, let's say the domain is the set of x values for the expression. Now, we looked at domain and range. The range is the set of y values for the expression or for the function. The domain is the x values for the expression or function. Now, what's interesting about these particular functions is that not every single number in the domain is going to work. So when you have a rational function, everything is going to be in fraction form. And whenever you have 0 in the denominator of a fraction, if you were to divide it with your calculator, it'll tell you divide by 0 error. It'll say that it does not exist. So that's what we're going to be seeing in these types of problems. We're going to be trying to figure out when the different numbers will work for these rational functions. So in a rational function, the domain will not include any value that makes the denominator equal to 0. So remember, you cannot divide by 0, like 3 divided by 0 does not exist. So when we're going to be seeing these problems, anytime the denominator of the expression we see is equal to 0, it'll make that entire thing not actually exist. So that's what we're going to be finding first here in section 6.1, the domain of these functions. So here's the formal definition of a rational function. So they give you two different polynomial functions. They call them u of x and v of x. The function f of x is when you divide one of them by the other one. All right, so that's kind of like the formal math definition of a rational function. It's when you have one polynomial divided by another polynomial. And the domain of these types of rational functions will work for every number unless the denominator is equal to 0. So in these examples here in the beginning, they're asking us to just find the domain, not the range. We don't ever have to really worry about the range. We're just looking at the x values to see what numbers for x will work and what numbers for x will not work. So here are the basic steps to finding the domain for functions. The domain will always work unless the denominator equals 0. So we're basically, in step 1, trying to find when the denominator equals 0. Because whenever the denominator equals 0, that means that that function will be dividing by 0, and dividing by 0 will give you an error. It does not actually work. So to find the domain, what we will do is look only at the denominator. The numerator doesn't matter at all. We only look at the denominator. When this denominator equals 0, it will not work. I'm just going to write it will not work. And mathematically, like, it does not exist. But I'm just going to say it's not going to work. So what we have to do is figure out what number will make that denominator equal to 0, and that's the only number in this case that will make this thing not work. What number will x be that would make the denominator equal to 0? 2. And that's because 2 minus 2 equals 0. So what you're doing is you're taking the denominator and you're setting it equal to 0 and then solving that little equation by adding 2 to both sides, and we get here x is equal to 2. When x equals 2, this will not work. And I can show you why. For looking at this function here, if we have x is equal to 2, this will say 4 over 2 minus 2, which equals 4 over 0. This does not exist. 4 divided by 0 does not work. So what happens when you're finding the domain of the functions, you are basically finding all of the numbers that will work except for, in this case, the one that does not work. The way that we write it can look 2 ways. One way to write the domain would be just to list the number or numbers that don't work. So sometimes you might see, like in today's practice activity, the domain, instead of listing it in interval notation like I'm going to show you second, it's going to show you just listing the numbers that don't work. And to show numbers that don't work, you write x is not equal to, so it's like an equal sign with a line through it. X just cannot equal to 2, and that would be it. Sometimes there is more than one answer that can't equal. To this example, it's just x can't equal 2. So that's one way to write the answer. The next way to write the answer is through interval notation. So here's one way. I'll write interval notation up here. So interval notation, if you remember back when we were learning about linear inequalities, we did some interval notation problems. Interval notation is very strange because you have to use all of these different formats and different things that we don't use that often. And you're going to have to understand how to do both, so this is just like a little refresher. The only number that doesn't work is 2. So if you're thinking about every number that exists, you can't obviously list all of those numbers. So interval notation shows you all of the numbers using this format. And the format is a parenthesis and then a negative infinity sign, comma, to the number that is the number where it doesn't work, and it doesn't work at 2 here. Okay, so I would write from negative infinity to 2, and parentheses means that it's not included, and 2 is not included, and that's why I'm using a parenthesis. If you remember, a square bracket shows that that endpoint is included and 2 is not. So it would be from negative infinity, any negative number, all the way to 2, not including 2, and then also starting back here at 2, but not including 2, to positive infinity. Now, if you're looking at the interval notation answer versus the other answer I just showed you, the first one's way easier. You just list anything but 2. This interval notation answer is saying it can be any number but 2, but it just shows it in a long, different way. You will have to understand how to do both. So here's your interval notation answer, and here's just the regular any number but 2 will work. So the first step in trying to find the domain is trying to figure out when the denominator equals 0. So when I look at the second example is g of x equals 2x plus 5 over 8. So you just look at the denominator for now. And the only way the denominator can ever equal to 0 is if there is some sort of variable. This is just a plain 8. 8 will never be able to equal 0 because there's no variable that could make it equal to 0. So because of this will never equal 0. So since this will never equal to 0, that means that the domain for the second one is every number. Every number will work. There is no number that will not work for this problem. So an easy way to say this without having to use interval notation would be like the domain is all real numbers. Okay, so that's one way to write the answer. Another way to write the answer using interval notation is not that bad, actually. All real numbers would be any number from negative infinity to positive infinity. So I would use a parenthesis, the negative infinity sign, comma, the positive infinity sign like that. So here's the two ways you could write your answer. All real numbers like that, or listing in an interval notation would be from negative infinity to positive infinity. Okay, so to find the domain of functions, we have to figure out when the denominator will equal to 0. In the next two examples, we actually have practice problems that are going to be a little bit different because they are not in factored form. In the first two problems that we saw, the denominator was either already in a form that would be considered factored, or it didn't need to be factored at all. In these two examples here, as soon as I see x squared minus 16, I should be thinking to myself, I can factor that. As soon as I see x squared minus 2x minus 3, you should be thinking to yourself, I can factor that. Because what you will be doing is figuring out when these two things will equal to 0. So your whole goal in finding the domain is looking at the denominator and figuring out when this thing will equal to 0. So if you see that, this looks like the last couple of questions we took the quiz on for the last chapter. This is solving those equations for 0. That's the whole point why we did that, is because now we're going to be able to figure out when these numbers will equal 0, which would make it not work for these functions. This is a difference of squares, since x squared is a perfect square and 16 is a perfect square. To factor this, I would factor this into x plus 4 times x minus 4. So when you have something that is factorable, you have to factor first. So in these examples, the first thing we have to do is factor the denominators. After you factor the denominator, then you can figure out for each part when it is going to be equal to 0, which will make it not work. So then you're basically using the 0 factor property to find when the denominator, I'm going to abbreviate DEN, equals 0. And I know that it takes a long time to write these notes to the side, but I think the steps are really helpful. So when you look back, you can actually figure out what you were actually doing in these different problems. So the first thing that we're going to do is look at only the denominator. We want to know when the denominator equals 0. And I see x squared minus 16 equals 0. I know I can factor that. So I factor that into x plus 4 times x minus 4 equals 0. We already know what to do here. We did this in the last chapter. We're going to set x plus 4 equal to 0. And x minus 4 equals to 0, we're going to get two answers. This one's going to be negative 4. This one's going to be positive 4. That means the domain for this problem will work for every number except for when x is equal to negative 4 or when x equals positive 4. So one way to write this is and what's weird about this is when you're solving these problems for when it equals to 0, it actually means that these numbers can't be those numbers. So I know it looks like x is equal to negative 4 and x equals positive 4, but that means that the domain cannot be equal to negative 4 or 4. So here's one way to write the answer quickly by just writing that the domain cannot equal these numbers. The longer way is using interval notation, and interval notation is annoying when you have multiple answers because you have to write each part of the number line. Basically, the domain, if you're thinking about a number line, it's any number except for -4 and +4. So it's any number on this side, it can't be this number, it can't be this number, any number in between, or any number on this side. So you have 3 separate parts when you use interval notation, which is quite annoying. The smallest number that the domain can be starts at -infinity, and then it goes to -4 and stops. And then it can be, but not including, anything from -4 to 4 and then stops. And then it can be from any number from 4 to infinity. You're probably thinking, that's crazy. And yes, that's called interval notation. It's definitely used in pre-calculus. You use these U's in between it to connect all of them together. That would be the interval notation answer, which is something that we did do previously, but you're probably thinking, wow, I haven't seen this in a while. I personally like just answering the 2 numbers in this case that it can't equal, and you probably are feeling the same way. All right, the second problem, the first step is factoring the denominator. So I see x squared minus 2x minus 3. I know that this number here is a 1, so I'm kind of happy because this is the quick and easy factoring problem. So I need to figure out, okay, what multiplies to be -3 and at the same time adds to be -2? So in order to multiply to be a negative, I know that my factored form will be one positive number and one negative number. The factors of -3, I'll just say +3 for now, are just 1 and 3. And in order to get a -2 from that, if one is positive, one is negative, I need the 3 to be the negative number. So that means this factored form will be x plus 1 times x minus 3. I'm just quickly verifying that in my head to make sure I didn't make a mistake, because if you put the 1 with the negative sign and the plus with the 3, then it's going to be opposite answers. So this factors to be x plus 1 times x minus 3. So I'm going to try and figure out when these things equal to 0, because that's the only 2 numbers that this function will not have in its domain. So I separate it into 2 separate equations, x plus 1 equals 0 and x minus 3 equals 0. I'm going to stop showing all the work for this part because it's just -1 plus 3. I'm going to get -1 and 3 as these 2 answers. What this means is the domain cannot be equal to either one of these numbers. And that is because when the domain does equal these numbers, it makes the entire fraction in the denominator equal to 0, and you cannot divide by 0. You will get an error. So the easy way to write this in just listing the domain as what numbers it cannot be, x cannot equal -1 or +3. Using interval notation, you have to think about all of the parts besides -1 and 3. And this gets annoying because with each number that the domain can't be, that gives you like another area in between those numbers. So there's like numbers less than -1, there's numbers in between -1 and 3, and there are numbers greater than 3 that are all part of the domain, which is why listing what it can't equal is the better way to do it. But I will show you the interval notation will be from anything from -infinity to -1, and then anything from -1 to 3, and then anything from 3 to +infinity. That's what the interval notation would look like. Sometimes we're going to see problems and we're going to factor it and we're going to have 4 separate answers. It's kind of silly to do that and have 6 things as interval notation. I'd rather just list the numbers that it can't be. So I'm showing you the interval notation because that's what the practice problem is asking you to do, but for a lot of them, I would just rather you write what numbers it can't equal. All right, so if you flip this over to the next page, we have some practice problems. There's just some notes again here. Same thing as before. The domain of a rational function is the set of all numbers which the denominator does not equal to 0. In example 1, it wants us to find the denominator of each rational function. when you're doing this, you are only looking for the denominator and when that denominator will equal 0. Letter A is actually the same exact one we did before, so I'm going to skip it. I'm going to start right with letter B. It says 4 over x. What number would make the denominator equal to 0? 0. So that's, I know it's kind of weird, but you look at the denominator, you set it equal to 0, and it's just 0. That means that the domain cannot equal 0. And if you're cool with this, I'm just going to leave the answers as just what it can't equal. So the domain means that x cannot equal 0 for letter B. For letter C, you look at the denominator, factor it if it needs to be factored. This one cannot be factored. So you just set it equal to 0. You solve that equation, and that means that the answer would be whatever number that is. The domain cannot be that. I know it's kind of weird. So we're going to get x equals 2 for this when I solve it. That means that the domain is every number but 2. The domain cannot equal 2. That's because when 2 is being inserted in for x, you're going to get 2 minus 2, which is equal to 0, which does not exist. You can't divide by 0. Okay, letter D, the next one, is that the same exact one as before? We're going to skip letter D. It's the same thing. Letter E, though, different. I'm looking at the denominator, x plus 6. X plus 6 cannot equal 0. So to figure out what number that would be, if you need to, set it up, solve it. You get x is equal to negative 6 when you solve. That means that the domain is every number but negative 6. X cannot equal negative 6. Okay, and we're actually going to skip letter E because this is something that we didn't necessarily learn. This has to do with square roots, so we're going to skip that for now. What I want to do is give you